All right, let's start. So there are three parts to the chapter. The first one has to do with history. The second has to do with atomic structure, ions and isotopes. And the third part has to do with nomenclature. So tell yourself, let's go ahead and as much as you remember, if you remember a lot of this, we don't have to do a lot. We can go a lot faster with some of this. All right, so the first name, when you run across here, the first name that comes across is Democritus, and they spelled it that way, or you can spell it the way you have it in your packet. And this person is not really a scientist. But back then, when you had people who, if you had a culture that didn't go to war all the time, you actually had time to develop a thing called culture. But if you're, like nomads don't have as much culture because they're constantly moving from one place to another. And their culture is very small. But if you have people that are not nomads and they're not going to war all the time, they have time to develop art and music and poetry and stuff like that. So, and also to develop things like thinking. If you think about the Greeks, they did have people that sat around and they thought about things. And so you hear about people like Aristotle and Plato and stuff like that. So Democritus was sitting around and they just asked a question. What do you think things are made of? And they wouldn't have known that, but they said, what do you think? And usually, like in 10th grade, I would probably pull out a piece of something. I think I'll use this one because that's aluminum. So let's say they had a piece of aluminum. And you say, well, what do you think would happen if I cut it in half? And you think, well, I think each half would still be made of aluminum. Let's do it again, and let's do it again. And they had this thought. It was just a thinking thing. What if you kept cutting it in half? Would you always get aluminum?
Yes.
Well, there was a group of people that said, no, I think matter is infinite. That means, yeah, keep cutting in half to infinity, you're still going to get aluminum.
Yeah.
And other people thought, no, matter, I think it's finite. They had no science to back this up. They just thought it was finite, meaning, I think there's a point where if you cut that last thing in half, it's not going to be aluminum anymore. They had no science behind it. It's just the way they thought. And so what word came out of that, and the reason we hear Democritus' name in a book, because whoever led the charge for the infinite matter, we don't think that's true. So Democritus in the book, the other person not in the book. And so what did he do? He used this term, atomos. Atomos meant what? And in his opinion, it was called indivisible. Okay? Indivisible means you can't divide it. So he thought there was a small particle that you couldn't divide. That means matter was finite. And that's really the only reason that Democritus shows up in a lot of chemistry books, because the word atomos became the word atom. And later we discovered that we think there are little particles called atoms. We also believe, if I take, let me have your attention, okay? We also believe today that if you took one aluminum atom and you cut it in half, would it still be aluminum?
Yes. An atom?
We don't believe that.
No.
And that's why Democritus is in here. Because if you took an atom of aluminum and you somehow were able to cut it in half, it couldn't be aluminum anymore because it wouldn't have the right number of protons, would it?
Carbon and nitrogen.
So he wouldn't have known that. He would not have known about protons or anything like that, but that's why we think matter is finite. Now, Democritus might have said, you can't divide it. We figured out, you can, but you're right. If I do divide it, I don't have aluminum anymore. So matter is finite as far as atoms in this case. All right, anyway, you move on, and the article you're reading, I gave you a little bit of time yesterday to read it, and that's, you're going to give me a one-page summary on that by Friday. Have you gotten anything out of that yet?
Yes.
What are these people? An alchemist, it's not one group of people. You're talking about almost 1,500 years. Isn't it a group of people, and they pass some of their information to the next group and the next generation, don't they? So you're talking about generation after generation after generation of people. Those are the alchemists. Now, if all the alchemists said, I'm not telling anybody my secrets, then it would have been gone. But they must have passed it on, and then they improved upon it, and they kept improving upon it. And a lot of books will say alchemists they were just messing around. But you should find out that alchemists did a great deal to further the study of chemistry. Now, we don't call it modern chemistry. but we do believe a lot of things they did helped us form the foundation of chemistry. Anyway, let's move on. And who they call the first chemist? Yes.
How would an alchemist make money?
How could it be what?
How would an alchemist make money?
Okay, now, the article that you're reading has to do with, I know one part of it has to do with crucibles. Has anybody read that yet? Okay, now crucibles, they knew that if you had a bowl-like thing that could withstand intense heating, I'm talking about putting it on a fire, maybe put bellows on it, intense heating. They thought some forms of matter will change if you get them really, really hot. So for an alchemist, a crucible was an important thing to have. Now, what if you made crucibles that were the best crucibles in the world? Other people might want to buy those. That's one way of doing it. Another way is, what if you had a king or a queen and they said, you're pretty smart and you might discover something that could help me defeat my enemies? Could you perhaps be hired by them and say, do this? And did some alchemists have to get into non-scientific things to make their money? It's possible. I think the whole idea, can I, Mason, since you brought this up, I'm going to bring something. Do you know that every scientist that we hear about in history, were they all rich to begin with? Some were. Some had a family and they had money. And some worked for a king and they had everything they could need. But some were incredibly poor. And to me, Mason, your question is even better to say, why would somebody who doesn't, kind of poor, doesn't make that much money, why would they spend time doing this stuff when they could go out and get a job and make some more money? They had a job, but they could make more money. And to me, that's the whole idea of human curiosity. That's something that God gave all of us. And why in the world would you go across an ocean and it's going to take you 3 months and maybe you'll hit land? Who would do that? Who would get in a spaceship and try to go to the moon? Who would do that? Why do you want to climb that mountain? Just look at it. No, I need to climb it. Why? So what a great question, Mason. I would say some of them did make money. I will agree. Some alchemists did probably cheat people. They probably said, here's something. If you drink this or eat this, you won't have that disease anymore. And there might have been a few people that didn't get the disease. They actually got cured, and then the word spread, and, that's called anecdotal data. So, all right, let's move on. As you go on, they said the first chemist was who? Now, and this guy, Robert Boyle, what he did was he started saying that we've got to start making science and chemistry. By the way, Boyle, back then, when you were a natural philosopher, you didn't necessarily specialize. Robert Boyle is known for Boyle's Law, isn't he? What was Boyle's Law? And didn't it have to do with pressure and volume?
Yep.
Yeah.
Anyway, so Boyle's Law is a really big physics thing, and yet Boyle's called the first chemist. Well, that's what they did. If they had a question they were trying to answer, they explored it. It might be in the world of physics, it might be in the world of chemistry. But one thing that Boyle did was he was trying to say, we got to start saying that if you don't do it with an experiment, if your experimental evidence doesn't show it, then we're not going to call it true anymore. Before that, there were so many things that were called true. And now they're saying, no, let's make sure if we can't do an experiment to prove it, then we're not going to call it true. And that's when you say that's modern chemistry. Okay, let's move on. Over here, there's some more names here. I'm going to do a couple more. On this screen over here, do you remember in the 10th grade there was a video and there was a guy named Joseph Priestley? Do you remember that?
Yeah.
There's a pretty good video where he was a dabbler. Remember that? He tried this, he tried that. And then he goes to dinner. He gets invited to dinner at the home of Lavoisier. And even though there's an interpreter and things, this guy here, Priestley, he's telling everything. hey, I did this, I did that. He's telling about everything he did. And some of these people like Lavoisier said, really? And so what happened is, who actually did discover oxygen? Lavoisier publishes a paper saying that he did, Lavoisier did. And he never mentioned Priestley's name, even though it was Priestley at a dinner who told him, if you do this and this, you can get this air that is better than air. And that air was actually oxygen. And so later, the history books gave credit to Joseph Priestley as the discoverer of oxygen, right there. And then one more, and then we'll stop. Lavoisier he did have money. And as a matter of fact, he had more money because he became part of the French government, and it had to do with collecting taxes. And of course, people don't like tax collectors. They constantly, if you don't give me the money, I'm taking your house away. Or if you don't do this, you go in prison. So people didn't like it, but what Lavoisier did is he was very meticulous, and even though he would do his work during the day, he also had a laboratory that he furnished, and he got the French government to pay for probably the best balance that had ever been made in the world. And it made it in England, but he bought it, sent it to France. And when Lavoisier did experiments, that's why he came up with the idea of the law of conservation of matter. He knew that if you had 5 grams of this and 6 grams of that, and you put it together and you didn't let anything escape, the whole thing's going to weigh 11 grams. And before that, they didn't believe that. They believed that there were these things, one of them was called phlogiston. They thought there were some things that every chemist knew was wrong. The stuff that was in the chemistry books back then, they said, when you take a piece of metal and you heat it, what happens to it? And the books, everybody knew that the metal actually got heavier. Now, why is that? If you heat a piece of metal, why was it getting heavier? Now, the phlogiston theory said that phlogiston was a real material, and phlogiston could flow into a material, it could flow out of a material, and yet that one thing about why would metals increase their mass when you heat them? Because heating them would sometimes drive away this stuff. They even had a thing called calorique. So anybody know? Why would the metal gain mass?
After being heated?
Yeah.
Was it because it was combining with oxygen, carbon dioxide?
It did.
Called it.
So aluminum has a mass, but aluminum combined with oxygen, aluminum oxide, would have a greater mass, wouldn't it? And yet they knew that was the case, but the textbook said that when you heat things, they lose mass. But they knew they had evidence that that was not true, but they just ignored it. It was almost like they had the perfect model, and this thing got in the way, let's just ignore it. Okay, well, that's enough about history, and we'll do a little history every day. Let's take your packet now. Let's go to the next part. Now, what I'm going to do is, you're going to tell me as much as you remember, and then we won't have to spend as much time with it. Let's take a look at what we think atoms are made of, and we'll just start. You just tell me what you know, and just raise your hand, and we'll just keep going until we. You're actually going to help me fill this out. So tell me, who wants to start? Who wants to start on? You can tell me about everything you know about protons, everything you know about electrons or neutrons. Who wants to start?
6 protons.
Wait, are we like filling it out? Trying to
Well, I want to know about 1 proton for right now.
Wow.
All right, who wants to start?
1 AMU.
Okay, which one?
That,
You doing proton?
the left one.
Are you doing proton?
Yeah.
Okay, all right, everybody look up here. The mass is an incredibly small number of grams. It's a very small number of grams, like 10 to the minus 26 grams, right? But because chemists are humans, they probably said, you know what? Why don't we make up our own mass unit? And why don't we call that incredibly small number of grams, like 10 to the minus 23rd grams, why don't we call that 1 AMU? Now, one atomic mass unit is the mass of a proton. Okay, Owen, you want to give me, do you know any of the other masses? Let's go around the room. Let's start, McKinley, you start. And let's go around the room and tell me any of these boxes you think you can fill in.
All right. Wait, am I starting?
Yeah, you can give me any box you want.
World of charge for protons.
Okay.
Positive.
What do you got?
Positive.
How much?
Plus one.
Okay, now, we talked about this in the 10th grade. There's actually a thing called coulombs, and coulombs are used to measure charge. Everybody got it? Now, the number, I don't memorize that number, but it's a very small number of coulombs of charge. But the scientists said, you know what? Why don't we call that bundle of charge, that many coulombs, let's just call it 1. Okay, that's 1 unit of charge. Okay, what else? Going down?
The protons are found in the nucleus.
Okay. Okay, next.
The mass of an electron is basically 0.
Okay, it's essentially like 0, and I will tell you the last number I saw was 1/1866 of an AMU. Now, if you put that in a calculator, 1 divided by 1,866, you get an incredibly small number, don't you? So it would take so many electrons to equal the mass of 1 proton, we essentially can say it's kind of like 0. Yes?
It's approximately 5.35 times 10 to the fourth.
Times 10 to the what?
To the fourth.
Well, look at you.
5 point what?
35.
Wasting your time.
Times 10 to the fourth, negative fourth? So anyway, if we wrote that out, 0.0005, I'll round it off. You can see it would take so many electrons to equal 1 proton that we don't have any elements that have that many electrons. We don't have that many that have half that number of electrons, right? It would take 1,000 electrons, more than 1,000 electrons to equal a proton. So who has more than 1,000 electrons here? Nobody. 118 is as far as we go, isn't it? So for the most part, in the world of mass, I really don't consider electrons when you're talking about the mass of the atom. All right, let's go on. Mason, you can do this one, this one, this one, this one, whatever you want.
So it's going to be a -1 charge.
Okay, now, what happened is, unbelievable, this thing in the mass world is like nothing. But in the charge world, it has the same number of coulombs as a proton. But, just like all physics, here's what happened in physics. You got 2 magnets. Let's say you had 2 magnets, ready? And these 2 ends attract, you flip it over, and then these repel. Who's north and who's south? There is no real north and south. A human had to come up with a test. If you do this, I'm going to call you north. Here's what they did. They did tests like that. For example, if I rub a glass rod with some rabbit's fur, and that's what they used back then, if that is going to be a positive charge. Now, if you're repelled by that, then you're positive. If you're attracted to that, then you're negative. And they had to come up with a definition for plus and minus. This could have easily been reversed. So we're not worried about, this is +1, this is -1, but the thing they have the same charge is the thing remarkable. All right, next. Well, you can do anything you want.
Wait, am I still?
Yeah, wait, you did -1, right?
Yeah.
Okay, Jeff? Do you remember anything? And if you don't remember it, I'm fine with that. I'm reteaching it.
Yeah, what is the question?
This or that. Or that.
I don't know the location of the electron.
Yeah, nobody does.
Oh, it's missing.
Because it's everywhere.
It's missing in action.
It's
MIA.
It's revolving around the nucleus.
No, we don't know that at all.
It's vibing.
Now, I will tell you that when we get to quantum mechanics, we don't really know at all what the electrons are doing. We just know where they're at most of the time, but we don't know what they're doing. And nobody likes that. Nobody likes that, but I will tell you they're not really in the nucleus, but they're in zones around the nucleus. We don't have no evidence that they're going in circles at all. We don't know that. Okay, next.
It blew.
Which one?
It blew.
All right, neutron what?
1 AMU?
Okay.
Question mark, question mark? Dot, dot, dot.
Now, if you go deeper into nuclear physics, if you look it up, you will see there is a slight difference between a neutron and a proton. Yes.
Your screen's frozen.
It's frozen? Okay, sorry.
She switched on the projector.
I did.
Okay. All right, ready? So there is a slight difference, and the neutron is slightly more than AMU, but really for most purposes, they're the same. And I think that's pretty amazing. You'll find out later. Later, I'll actually tell you why the neutron is slightly more than the proton, but not for right now. All right, who's next?
Olga.
You already did one, so I'll skip you. How about that? Yeah. Which one you want to do?
I'll do the charge of the neutron.
Okay, go ahead.
Really?
It's neutral.
And again, that's why they call it the neutron. It was neutral. It was neutral in charge, so that was no charge. Now, remember,
That's what a neutral
I tried to teach this in 10th grade as well as I could, that you can't cross that line, that ball. Your brain has to say, in the world of mass, protons and neutrons are everything.
Yeah.
But in the world of charge, protons and electrons are everything. So you can't mix those two up. And these are also in the nucleus. So therefore, we know that protons and neutrons are called nucleons. I'm seeing people use that word a lot more in textbooks. A nucleon is any particle in the nucleus. That's protons and neutrons. So those are nucleons, right? All right, let's go down here. And again, I'm going to go as fast as I can. And I need you to understand it, though. You can't shake your head if you forget it. You just say, tell me, I don't know that one. So here is a terrible model of an atom, but it's a good model of the atom. How can it be both?
Because it's
And-
so big.
Right. So in the world of science, we build models all the time. Models are useful until they reach the limit of their usefulness. And every model has a weakness. Every model has a weakness. Now, if I, like in the 9th grade, and maybe even in the middle school, I would use the Bohr model. This is called the Bohr model. Bohr, who was actually a student of Rutherford, yes,
Did you have a particular element named after him?
borium. But borium, now, anyway, and Rutherfordium, he was a student of Rutherford, but Bohr, he had this, he was actually one of the first people to think that electrons were not anywhere, but they were in different places that he called, it took a certain quantum of energy to move it from one level to another. And that's where the first time they used the word quantum. But where he was wrong was he believed that the electrons did go kind of in orbits around the nucleus, and then they would jump one orbit to another like that. What a beautiful model back then in the late 1800s, early 1900s. But it was proved later to be, we have no idea like that. And as a matter of fact, his model fell apart. When it applied to a hydrogen atom, it worked beautifully. Any atom that had more than one electron, he couldn't predict what was going to happen. It was not a good model, so they eventually abandoned the Bohr model. Why do we still teach it sometimes? Because here, at least the atom sitting still is static, and I can look at the nucleus and I can look at the electrons, and so for this, it's a good model. But it's a terrible model for distances. I'm going to see if I can find that number for you here. Yeah, here it is. Take a look at this number here. Here's a model of an atom, and it says that the outer regions of the atom might be a total of 10 to the minus 8 centimeters. Is that very big?
Oh, wait, eight?
No.
Well, first of all, a centimeter is this,
To the
and
minus.
10 to the minus 8 would be 100 millionth of this. So anyway, it's pretty small. And there's the atom at 10 to the minus 8. And how big is the nucleus?
It's not that big.
10 to the minus what?
13.
13. Now, think about that. If I had to make a model of an atom, I'd have to make the nucleus 5 powers of 10 smaller than the atom. So if I made an atom this big, a model of the atom this big, what's 10 to the 5th? Isn't it 100,000? I'd have to make the nucleus 100,000 times smaller. You almost wouldn't see it. If the atom was this big, I probably wouldn't even see the nucleus. And that came up with a lot of people's work, Rutherford for one of them. So this is a terrible model as far as showing size. But it's a good model for me to look at the particles and learn some vocabulary words. Yeah.
So what occupies all that space?
Okay, now, when I was your age, that bothered me because I didn't understand what they meant when they said nothing. And nobody likes to say that. What is in between the nucleus and the electrons? And everybody likes to say it must be air. But what's air made of? It's made of atoms, isn't it? It's made of molecules or made of atoms. But so what's nothing? And that made all kinds of physics people think about that. There are people thinking that there's no such thing as nothing, and they make up things like, is there something where there's nothing? So right now I'm going to say nothing. Nothing. It's nothingness, emptiness. No matter at all is in between them. So let's go over here, and even though it's a bad model as far as size, let's take a look at it. And if we could stop an atom in its tracks and say, stop right there. Let me look at you. Now, enlarge the nucleus. What I see is, I see 3 protons. What does that mean? Well, that's how I'm going to identify you. It's like a fingerprint. If you have 3 protons, you must be what?
Lithium.
You have to be lithium. Now, we didn't know that at one time. We did not know that the different atoms, different elements had different number of protons. We didn't know that. We know it now. So the atomic number is the number of protons, isn't it?
Yeah.
You'll never get fooled with that. That is the fingerprint. Whether you're an ion or an isotope, if you have 3 protons, you're lithium something. Are you with me on that?
Yeah.
Okay, so now, next, the mass number is the number of nucleons. So look at a nucleus. How many things are nucleons? 3 protons, 4 neutrons. There are 7. There are 7 nucleons. Now, the way that a chemist would represent lithium, I'll go down here now. Here's lithium, but I want to tell you, be more specific about lithium. Everybody should know that lithium, and a lot of times they don't put that number because you're supposed to have a periodic table, and you knew that lithium was number 3. Why is the atomic number 3? It's the only kind of atom in the universe with 3 protons. That's what goes down here. So what goes in the lower left-hand corner is the atomic number. That's easy. What goes up here is the mass number. The mass number. Now the mass number for this guy is what? 7, right?
Yeah.
And so here's, this corner is reserved for the world of mass. This is for the identity, your fingerprint. And this is how you do isotopes. Isotopes are atoms of the same element, but they have different masses. For example, watch. What if this lithium only had 3 neutrons? Then you'd have to write it as lithium 6, lithium 5. And these are called isotopes. Is everybody with me with that?
Yeah.
All right. So I didn't change the fingerprint. The fingerprint says you're lithium. You're still lithium, aren't you? But this little number here tells me how many nucleons you have. Now, what if you took the mass number minus the atomic number? What's the mass number minus atomic number? Say it. Number of neutrons. Now, look up here. That's different. That says 6.9 something, doesn't it? Now, what is that called? That's not the mass number. What is it? atomic mass. Now what that means is some lithium atoms might have a mass of 6, some might have a mass of 7. And I have this machine called a mass spectrometer. I'm going to measure 2 million lithium atoms. And I'm going to tell you what percent of them have this mass, what percent have this mass. And then, guess what I can do? Just like on a quiz. If you have 2 quizzes with this score, and 2 quizzes with this score, and 3 quizzes with this score, you're going to get a weighted average, aren't you? And that right there, there are no lithium atoms with a mass of 6.9. None. But that's the average mass of the isotopes, and it would be a neat project for some of you. I know some of you could do this. Try to find a real periodic table from the 1850s, 1870s, 1900, 1920. Try to find real periodic tables and take 10 elements and find out whether the the atomic mass is different. And they will be. Why would the atomic mass have changed over time?
Technology.
What?
Technology.
Yes. And so at first, how did they find the mass of any atom? That was pretty crude, wasn't it? It probably with a balance. Anyway, thank you very much. Right. So it'd be neat to see what did the periodic table, what kind of numbers did they give you if you could find even 4 of them, late 1800s, early 1900s, 1950, and 2000. It'd be neat to see if any of them changed. And it'd be hard to find out, what technology did it. The mass spectrometer for sure did that. All right, are you okay on this? So isotopes are the world of mass. Notice I'm not even going to do the world charge right now. I want you to let it soak in and do the world of mass. Let's go over here and turn the page. Again, these are Bohr models. Terrible for size, but it'll do what I want it to do. What's the atomic number of this model? These are 3 different atoms, aren't they? There's no way those are the same atoms. All right, what do you think? What's the atomic number?
1.
How about this one?
2.
How many?
1.
That's right. How about this one?
1.
Therefore, if that's the case, the only element that has the atomic number 1 or 1 proton is hydrogen. They have to be hydrogen. They have to be hydrogen. They have to act like hydrogen. They'll explode if you try to light them. You can make water out of them. Some of the water is going to be heavy water. Some of the water is going to be radioactive, heavy water. Now, let's go here. What's the mass number of this guy? 1. How much? How much?
1.
Oh, don't look at electrons in the world of mass, do you?
No, you don't.
Okay, how about this one? Okay, now, this would be very confusing to scientists, so they had a way of doing it. And I can put the 1 down here. That's not necessary, but I do need this one. I need that, I need that, and I need that. You see that? In the world of isotopes, that's what I'm going to use in my symbols. Atoms are the same the same element, but they have different masses. You know why they have different masses? Tell me that. Why do they have different masses? Look right there.
More neutrons.
Yes. More or less neutrons than the other one, right? I had a teacher, 2 different teachers in high school, and I thought it was telling me the truth. And they told me this was hydrogen, and these were isotopes of hydrogen. Can I tell you something before I go? Which one of these is hydrogen?
They're all hydrogen.
So which one's the isotope of hydrogen?
They're all hydrogen.
They all are. Okay, thank you.
Okay,